So I formally welcome all of you. It's really my pleasure to introduce Dr. Sara Varotto. And we are really privileged and very happy to see Professor Albert Fert with us. He is one of our regular audience, and I'm really grateful. He gave the 50th lecture, and he's always inspiring us. I'm very grateful to him. And yeah, good evening, good afternoon, good morning, wherever you are. It's the 91st webinar of this webinar series on spintronics. And today we have Dr. Sara Varotto. So little words about her career. So Sara obtained her PhD from Politecnico di Milano in 2016 in Italy, where she worked with Ferroelectric Rashba semiconductors. Then she joined the group of Professor Manuel Vives at Thales Lab in Paris-Saclay, where she pursued her experimental work on Rashba systems, and this time about oxide materials and interfaces. I think today's talk will be about that. And recently she has joined Chipron, a startup company which is developing revolutionary MRI machines, so very application-oriented research now. And with this brief introduction, I welcome you all. And I just mentioned that during the lecture, we don't take any questions. If you have any question, you kindly write in the chat box or raise hands. At the end of the lecture, we will first take a group photo, and then we will have the question answer session. So with this brief note, again, on behalf of the WPS team, myself, Braj, Puspendra, Shakti, Soyang, Ajay, and all the team, I thank Sara for accepting our invitation and giving this lecture. So it's all yours. Looking forward to your lecture. Thank you very much.
Thank you for inviting and for the introduction. So I will start by sharing my screen. Okay. I hope you all can see that. Here. Okay. Can you see my screen? Everything is fine?
Yes, it's all good. It's good.
Okay, great. So good afternoon and evening to everybody. Today I'm very happy because I can give a lecture about what I have done during my PhD and my postdoc. And the lecture will deal with multifunctional systems that combine ferroelectricity, which is an electric field effect, together with a spin-based effect, which is the Rashba effect. And I will show the basic concept of this basic phenomenon, and I will show you how we can use them to create some spintronic device that combines in-memory and logic together. And we will explore two different systems from chalcogenides to two-dimensional neutron gas systems in oxides. And the work that I will show is the combination of actually two works, the work I did in my PhD in Milan, under the supervision of Cristalina and Riccardo Bertacco, and a work that I performed during my postdoc in CNRS Thales here in Paris, in the group of Manuel Vives. And a large contribution also comes from SpinTech lab located in Grenoble, where all the spin to charge conversion experiments were performed. And so I want to thank them particularly. And of course, I want to thank all the collaborators and people I work with. So before starting, let me just take some little time for some advertisement. So I'm very happy that currently I'm working in Chipron, which is a startup located in Paris. And what we are doing is to solve a very important problem in the medical side, that is the lack of a safe and cheap and a diagnosis tool that can be accessed by everyone and with a very high quality images. And nowadays, this is done by a very high field MRI machine, magnetic resonance imaging. And this is clearly not accessible to everyone due to the very high fields that must be applied and the cost of this machine. And what we are doing is a portable version of this, which will be accessible to everyone and give the same image and completely safe. So if you're interested, you can check out our website or thinking of joining our team. So after that, I will move to the presentation. So today we are not solving the MRI machine problem, but we are dealing with another problem, still very important, of course, that is energy consumption. So information technology is consuming a big portion of the total electrical consumption. And if consider that we are now here in 2022, this is, you can see from this graph that the energy forecast predicts that the ICT will consume up to 21% of the total energy demand in the world in a few years. And of course, this is not sustainable. And this is the problem is related to the fact that nowadays computers are based on von Neumann architecture, in which we have a memory unit and a processing unit that are separated. And most of the electrical consumption happens due to the fact that we are moving the data between these two different units. So the solution is to change the paradigm and bring the memory and computing closer, ideally in the same device. And this will lead to logic in memory operation or scheme will remove the need of the data transfer. And so we have larger throughput and lower power consumption. So the question is it possible to make a sort of transistor that also implements the memory functionality? So spintronics offer the possibility to achieve this goal by using a multifunctional system that combines two properties. One property is the memory that can be achieved by using a ferroic order, for instance, of ferroelectricity or ferromagnetism, in which the ferroelectric polarization and the magnetization can be switched reversibly between two different states, up and down. So this can correspond to our bit 0 or 1. And ideally for our technological application, we want to switch this bit electrically. So we want a non-volatile, electrically controlled state variable. And the system, if it's endowed by spin-Rb coupling, can show what is called the Rashba effect. The Rashba effect leads, as I will describe more in detail later on, leads to a spin-dependent splitting of the electronic bands. And this splitting with this particular chirality of the spin leads to the possibility of converting charge current into spin currents and vice versa. And I will show you if we can combine these two concepts in the same material, in the same system, we can achieve in-memory spin logic. So very recently, Intel proposed a device, a basic device called Magnetoelectricsynaptic logic device, or MISO, that combine exactly this concept. And here I will show you how it works. So for, in this case, the memory functionality is implemented by the ferromagnet. So we store the bit 0 or 1 in the direction of the magnetization. And the readout, okay, and this memory is controlled electrically because we want to write it electrically. This is done by means of a ferroelectric or magnetoelectric that is coupled to the ferromagnet. So by switching the ferroelectricity in the green layer, let's say, we can switch the magnetization of our memory. So in this case, we have a spin memory controlled electrically by means of magnetoelectric coupling. And the readout of the memory is performed by the spin orbit coupling material, for instance, a Rashba system that allows to convert the a spin current that gives the information of the magnetization of the ferromagnetic layer into a charge current. So we will have an electrical output. And so we have, this is possible thanks to spin to charge conversion operated by spin orbit coupling. So let's see, for example, if now we invert the ferroelectric polarization, we invert the magnetization, and the spin that we inject in our spin-Rb coupling material will be opposite, and the current and the voltage, output voltage of the device is switched. So this is the way this MISO device operates, and it can be seen as a non-volatile spin-based transistor because we have a memory and the computation within it. The potential of such architecture is that we can, in fact, have a unique device that can implement both memory and logic. And since we have electrical input and output, we can concatenate it and think of making, in fact, the logic by controlling the next device magnetization by the output of the previous one. So in this publication, you can see, for instance, how they suggest the in-memory logic majority gate by using 4 of these unit devices. Also, this device is based on 2 transduction mechanisms, the magnetoelectric coupling and spin-Rb coupling, that are both scalable. So they show the scaling laws that allow to reach the future goals for efficient spin charge conversion, for efficient operation, bit operations. And in fact, they show that we can reach 30 times less lower power consumption compared to CMOS for the same size. So all this is nice, but this device has not been achieved yet. And this is also related to some technological challenges that are related to the structure itself. In fact, the structure is even more complicated than what is shown in these schematics. It requires many layers, many interfaces that have to be with different material that have to be optimized. And in particular, for instance, the magnetoelectric coupling is quite critical because in order to switch the magnetization by electric field, it requires quite, let's say, a large electric field. And so this imposes some limits in the operating voltage. In fact, it has been proposed as a goal to switch with less than 100 millivolts. So the spin-Rb coupling layer must generate more than 100 millivolts, which is really, really high. So what I will propose in this work is to change the structure, simplify the structure by using ferroelectric Rashba systems. And I will show you why. So let's first try to understand what is the ferroelectric Rashba system and why is it promising. So if we consider, for instance, a metallic interface between 2 materials or a metallic surface in which we have spin-Rb coupling of 3 carriers that interact with an external electric field perpendicular to the plane of motion of the carriers, a Rashba Hamiltonian will appear in the system that will add to the free electron Hamiltonian. And the Rashba Hamiltonian depends on the product between, let's say, the electric field and the spinor and the spin of the electron and the wave vector of the electron. If we solve the eigenvalue problem, what happens is that this the band structure will be the spin degeneracy will be lifted in the band structure. So the 2 parabolas for the 2 different spins will be, let's say, shifted pictorially in the reciprocal space. So the shift will be along the wave vector axis. And this is the, let's say, the formula for the amount of the splitting between the upper and the lower band. And this splitting is proportional to the wave vector, thanks to this proportionality coefficient, which is actually a field, which is called Rashba field, that depends on the electric field. It is proportional to the spin-Rb coupling and the electric field. So it means that if we change the electric field, we can change the amount of splitting that we have, and so the spin properties of the band structure. Another important, very fundamental output of that is due to the Rashba Hamiltonian is the fact that the spin is locked perpendicular to the wave vector for any point of the reciprocal space. So this means that we have a specific chirality for the 2 Rashba Fermi contours that we have at the fixed energy, for instance, the Fermi level. And as you can see, we have that the spin is always perpendicular to K and with opposite chirality for the inner and the outer band. This so-called spin momentum locking allows for the conversion between a charge current that can be injected in this direction into a spin current that is formed in the transverse direction. I will show you later what are the mechanisms that lead to such a spin conversion from the spin texture. An important point here is that if we change the electric field, we can tune the splitting, we can tune the spin texture and this spin to charge conversion. Let's come now to the ferroelectric Rashba system. So now we introduce this, an electric field, which is the ferroelectric polarization. So in this case, this electric field is permanent, so it's non-volatile, and it acts like we are changing this electric field. So if we change the polarization direction, we can change the spin chirality of the two Rashba bands. As you can see here, they rotate in opposite direction. So what is the consequence on the spin transport side is that if we apply a gate to switch the polarization, we actually generate opposite spin currents, as you can see here. So we can change the spin to charge conversion efficiency. So we can use this concept now. If you come back to the original Intel device proposed by Intel, we can try to simplify it by using ferroelectric Rashba systems, which is this purple-green layer. So the idea is now to store the information inside the ferroelectric polarization instead of the magnetization. And now, if we switch the polarization, we know that we are inverting the circulation of the bands and the spin to charge conversion efficiency. So for a given injected spin current, the red one, which is not changed because we are not changing the ferromagnetic direction, we have different output currents depending on the ferroelectric polarization. So this is a simplification of our scheme. In fact, we just need a ferroelectric Rashba system that in itself combines the memory and the computing functionality, because the ferroelectricity directly controls the Rashba spin-orbit coupling. And in this case, then we need just one transduction mechanism. We don't need the magnetoelectric coupling because we don't need to switch the magnetization electrically anymore. And we just keep the ferromagnet just to inject the spin current for the readout. So this is the power, let's say, of these ferroelectric Rashba systems, because they allow for logic in memory within the same material, not just within the same unit device as proposed by NISO. And this device is patented by our group in collaboration with SpinTech, and it's called Ferroelectric Spin Orbit Logic Device, or FISO. So in my talk, I will show you how we can deal with ferroelectric Rashba systems. Actually, I will talk about two different ones. The first category is based on two-dimensional neutron gases in oxides, in which we can form a metallic interface between two different oxides, for instance, a perovskite and another oxide. And I will show you, for instance, in the case of potassium tantalate 2DAGs, that we can observe a quite large Rashba splitting and very high spin charge interconversion efficiency. And in the second part of this first part, let's say, I will also show you how we can use the flexibility of the perovskite to introduce ferroelectric polarization that will couple together to the two-dimensional neutron gas to achieve this non-volatile control of the Rashba states. And then after this, I will move to a completely different class of material, which are semiconductors. In this case, the ferroelectric polarization is a property of the semiconductor because we have a permanent lattice distortion along a certain direction of the lattice, and this will create a Rashba effect in the bulk of the bands. So the bands of the semiconductor are Rashba splitted. And so I will show you the experimental evidence of this, so how we can actually change the Rashba effect in germanium telluride films by means of ferroelectricity. And in the last part, I will show you how we can achieve this ferroelectric control of spin charge interconversion at room temperature. So let's start from the two-dimensional neutron gases. What we need to know is that two-dimensional neutron gases in oxide and interfaces are quite important in spintronics, because they have high mobility carriers that, combined together with the Rashba effect, leads to efficient spin charge interconversion. So how we can create high mobility carriers so how we can create a 2DAG in an oxide? This is due to some electron doping that can be created by ion irradiation or by creating an interface between two different perovskite oxides. So for instance, between the very quite famous LaOSTO, so lanthanum aluminate, and strontium titanate. And they both can be grown by PLD, and they show nice structure epitaxy. And the two-dimensional neutron gas that is formed at the interface shows quite high mobilities of the order of 3,000 centimeters per volt second. And quite recently, a new method to generate two-dimensional neutron gases has been developed and proved several times. And nowadays, we are using this as a routine that is to make an interface between the STO, for instance, together with a reactive metal, for instance, aluminum, yttrium, or tantalum. This metal will oxidize by reducing the titanium, for instance, in the perovskite, and with the formation of oxygen vacancies, and such oxygen vacancies will populate a two-dimensional electron gas. So here you can see, for instance, the formation of the 2-deck from X-ray photoemission spectroscopy measurement. So the titanium, once we put aluminum oxide on top, will get reduced with the formation of titanium 3+ and 2+. And this reduction occurs at the interface, as shown by this angle dependence. So as much as we are surface sensitive, we are more sensitive. We can see that we have more oxidation, and so this means that we are actually creating this gas at the interface. And the second part deals with the Rashba effect. So I already introduced it, but I should just recall the fact that if we have a two-dimensional electron gas, of course we have symmetry breaking by construction, and so there will be an electric field perpendicular to the surface that will lead to such a spin splitting of the bands and such a spin texture. In STO two-dimensional electron gases, the Rashba spin-Rashba coupling has been investigated mainly by transport measurements and not has never been detected directly by means of, for instance, of spectroscopic techniques, because the alpha R, so the splitting, is very small. The alpha R is of the order of 50 millielectron-volt Armstrong. And although quite small, very, very small, combined with high mobility carriers, this effect is sufficient to lead to very efficient spin charge interconversion. And the mechanism is given by the so-called Rashba-Edelstein effect. So, for instance, let's consider the direct Edelstein effect. If we inject a charge current along one direction, this will lead to a delta K, so a shift of the Fermi contours with respect to the K equal to 0 of an amount delta K. And if so, by doing so, spin density will be created by the two Fermi contours, this red one and blue one, where the outer one will be larger in magnitude, in absolute value, compared to the inner one. So we have a net spin density generated by a charge current. And this can diffuse as a spin current if we attach some other layer to it, for instance. So the converse mechanism is also possible. So we can inject a spin current, for instance, by spin pumping, and generate a charge current. And this is achieved by the fact that when we inject the spin density, the two Rashba Fermi contours can accommodate this in the system by shifting in the opposite direction in wave vector space by forming another delta K. So this delta K will be linked to the generation of a charge current. The figure of merit of this mechanism is given by this length called the Rashba-Edelstein length, which is the ratio between the two-dimensional charge current and the three-dimensional spin current. That's why it's a length. And it's proportional to the product between this alpha R, so the Rashba parameter, and the electron scattering time. So if we want to get a very large lambda, we need a high mobility materials, which is the case with the two-dimensional electron gas. We need large spin-Rashba coupling in alpha R value. And here, the point is that alpha R will depend on the electric field. So we can increase or tune this lambda by changing the electric field by gate or by ferroelectric polarization. Here, I want just to show the values of the lambda, depending on the different systems, actually the highest values of lambda that are reported in the literature. So we have alpha 10, or we have LEO STO, for instance, of 6.4 nanometers, and the record value of an aluminum STO interface, which reaches 225 nanometers. Okay, so in my talk, I want to show you the results that we achieved in another system than strontium titanium, which is potassium tantalate, and I will show you why. So on one side, it behaves very similarly to the STO. In fact, we can define a two-dimensional electron gas by depositing some aluminum on top, which will get oxidized and reduce the tantalum peak and form the electron gas. So as you can see here, for instance, this is the result of the XPS measured on the KTO. And as you can see, the reduced tantalum increases as much as we increase the aluminum thickness. And this means that we are populating more and more our two-dimensional neutron gas as measured by transport. So we have a larger number of carriers in our gas. And also by measuring the mobility through MR and the Hall effect, we can extract two different kinds of carriers. Let's say a heavier and a lighter one with different mobilities. So we have quite high mobilities for one kind of carriers, like up to 2,000 centimeters per wall square. So it behaves quite similarly to the STO. However, in this case, the tantalum is quite heavier compared to the titanium. So we expect that the Rashba effect in KTO is much larger than in STO. And we investigated this by employing angular solved emission spectroscopy, ARPIS, in solid synchrotron, and we mapped the band structure of this two-dimensional neutron gas on aluminum KTO. So as you can see here, we have this band structure, which is cut at the Fermi level. So we have a two-dimensional neutron gas, and we observe different band pairs that are simulated and fitted by means of tight binding calculations. So we have different pairs: the purple, the green, and the orange, and this cyan band that nicely overlap to our band structure. And if we now focus on this inset, so in this zoom, we can now try to look really at the details of the band structure. And as you can see here, in both these panels, I reported the complete band structure measured with the maximum signal combining different polarization. As you can see, we have the formation of two branches here and here, here and here, that are fitted quite nicely by means of this orange band pair that has a Rashba split shape. And just to conclude on this slide, I want to just show you that these calculations are that these fits work quite nicely along the entire Fermi surface, because if we cut at the different energies, for instance, these three, we can have quite nice overlap with the tight binding fits. So for the first time, we could observe a Rashba type splitting on a two-dimensional neutron gas by ARPIS. And thanks to the fitting by tight binding, we can extract a Rashba coefficient of 250 megaelectron Ångström. This is like 5 times larger than what is observed in STO. And so we have a two-dimensional neutron gas with high mobility and higher Rashba compared to the STO. So what we did is to investigate the spin-to-charge conversion and charge-to-spin conversion in this system. So concerning the conversion from a spin to a charge current by inverse Ederstein effect, we employed spin pumping at ferromagnetic resonance that consists in interfacing our KTO aluminum to ferromagnetic layer, for instance, permalloy, that is brought to its ferromagnetic resonance. So when we excite the permalloy at its resonance by applying an RF field and a DC field, when we reach the resonance condition, we can inject a spin current across the interface, and then by spin to charge conversion, a charge current will be generated in the two-dimensional neutron gas that can be sensed by means of a voltmeter. So it's a relatively simple measurement. So these measurements were performed by our collaborators in SpinTech. And they actually measured the resonance of the nickel iron, for instance, this blue curve, and at the resonance condition, as you can see, we have that the charge current shows a peak, negative in this case. This peak means that we are injecting a lot, like the maximum spin current at the resonance, and we are creating the maximum charge current at this resonance. What happens now if we invert the ferromagnetic direction? So the saturation magnetization is that we are injecting now the opposite spin. So we invert this spin, and this results in a generation of the opposite voltage, so opposite charge current. If we now look at the value of this peak, we can compare it to the STO, and it's quite large, so it's comparable to the STO with a certain amount of doping, so a certain amount of electric field. Okay, and whereas this one is performed in remanence, so we are not applying any electric field. And quite for curiosity, we also observed that the sign is opposite compared to the STO, a low filling. So we think that we have a negative Rashba coefficient. Concerning the converse mechanism, so for the direct Edelstein effect, conversion from a charge current to spin current, we employed unidirectional bilinear magnetoresistance technique. So this consists in making a whole bar in which we inject a charge current. This will generate the spin density as shown here, and we can detect the formation of this spin density by applying an in-plane magnetic field. And depending on the orientation of the magnetic field with respect to the spin density, we can have either low or high longitudinal resistance. This method has been applied already in topological insulators or LAO-STO. And the important point here is that our collaborators, like Anar Dirdal, in collaboration with our group and Andersvet, of course, they developed a very simple and nice and useful model for this effect that allows to extract an effective Rashba coefficient. So just to explain a little bit more in detail about this technique, what happens is that when we create a spin density by applying an electric current, we can try to align it parallel or anti-parallel with respect to the external magnetic field that is rotating in the plane. And this will lead to a different effective magnetic field for the carriers that are moving inside our material. So according to the model, we have that the relaxation rates of the spin up and spin down carriers are different depending on this, are modified. And the resistivity is predicted to have some angular dependence with respect to the magnetic field. And in fact, in the resistivity formula, we have two terms. The first term is called unidirectional or bilinear magnetoresistance. And that depends as a sinusoid, a sine of phi, so the angle of the magnetic field with respect to the current. So it means that it changes sign when we are at 90 degrees or 270 degrees, so parallel or anti-parallel to the spin. And it's bilinear because it's proportional to the magnetic field and the charge current that we apply. And most importantly, it's proportional to the alpha that we want to extract. The second part is called quadratic MR, and because it scales quadratically with respect to the magnetic field. And it has a different angle dependence, which is cosine of 2 phi. The important point is that both of them scale proportionally to the scattering time, tau. So it means that if we can measure both of them and take the ratio of their amplitude, we can extract the alpha R by knowing the Fermi energy and the input current, the magnetic field applied. So we have employed this technique in a KTO aluminum sample. And this is an example of the curve that we measured for a fixed current direction. And by changing the magnetic field orientation in the plane. We observed the formation of two terms, the appearance of two terms. We have a sine of phi and a sine of 2 phi. And we can extract them by taking either the sum or the difference between two curves with opposite current. And as you can see here, by taking the difference, we get the BMR, which depends as sine of phi. And taking the sum, we can get the QMR, which scales as a depends as a sine of 2 phi. And the BMR term, amplitude, depends linearly with respect to the current and the magnetic field applied. So it's indeed a bilinear magnetoresistance, whereas the QMR scales quadratically with respect to the magnetic field. So we have pretty much everything that we expect from the model. Moreover, the sign of this BMR leads to a negative Rashba coefficient consistently with the spin pumping results. And finally, by taking the ratio between this BMR and QMR amplitudes, we obtain an effective Rashba coefficient that ranges between 70 and 320 millielectron Armstrong. That is much larger than STO and agrees pretty much with what is observed from the band structure. Okay, so up to now we have seen that with the KTO aluminum, we have high mobility, we have a large Rashba effect, and large spin to charge and charge to spin conversion. We want now to think how we can introduce ferroelectricity in this kind of system. So we want to move towards ferroelectric Rashba two-dimensional electron gases. Let's start, for instance, from the STO structure. We know that at high room temperature, it's a cubic structure, and it undergoes a tetragonal distortion below 105 Kelvin, which is still paraelectric phase. But when we reach very low temperature, it enters the regime of quantum paraelectric or incipient ferroelectric. This means that it's quite prone to become ferroelectric. It can be stabilized in a ferroelectric phase if we introduce some perturbation. One way is to dope, so substitute the strontium iron ions by means of other materials, for instance, calcium. And for calcium has been shown by Van Betnort in his paper that already with 0.25% we can stabilize the ferroelectric phase and at below 10 Kelvin. And these results have been reproduced in our group, shown in this publication. So we, with the calcium 1% doped STO substrate, we observe quite robust ferroelectricity below 25 Kelvin. And by creating a two-dimensional electron gas, as I shown you before, on top of these films, we can observe that ferroelectricity controls the sheet resistance of this gas. So we are modifying the electrical transport of this two-dimensional electron gas by ferroelectricity. Similarly, we can operate in potassium tantalate by substituting tantalum by means of niobium. What has been shown is also another mechanism. So it's possible to stabilize ferroelectricity in STO by means of an electric field large enough electric field, as described in this publication. So this ferroelectric state with a nice ferroelectric group is stable below 50 Kelvin, which is the critical temperature of the system. And what they have shown is by spin pumping at ferromagnetic resonance, once again, in SpinTech, and they've shown that the current production changes sign can be switched reversibly by changing these ferroelectric vectors, so applying a positive or negative voltage. And by changing this voltage, gate voltage in progressive manner, they obtain a hysteresis loop that reminds of the ferroelectric polarization. So this is the first demonstration of non-volatile electric control of inverse Edelstein effect in STO two-dimensional electron gas with two different remanent states. The main drawback, let's say, limitation of the application of such systems is the quite low operating temperature that is limited by the critical temperature of the ferroelectricity, which is 50 Kelvin. So in the next part, I will move to a different kind of materials that are ferroelectric at room temperature. So ferroelectric Rashba semiconductors not only embody the ferroelectricity and the Rashba effect that are interlinked, as we want, but they are also semiconductors. So they are directly grown on silicon, and the growth techniques are compatible with CMOS technology. So they are quite promising for the actual implementation in devices, let's say. They are closer to the application. So concerning the first link, so I want to show you the experimental proof that by changing ferroelectricity, we can change the chirality of the Rashba spin structure. So this, we perform all the experiments in germanium telluride, which is the father compound of first, is a ferroelectric at room temperature due to a lattice distortion that occurs along the 111 direction. And this leads to a different spacing between germanium and tellurium planes, which forms a ferroelectric dipole. And it's possible to switch the ferroelectric dipole by changing the distance, the relative distance between the germanium and tellurium planes in this way. And this has been shown in this very nice publication. And this permanent lattice distortion leads to a giant Rashba splitting of the bulk electronic bands of the material, as predicted initially by DFT calculations in this paper. And the splitting is shown here, occurs in the plane perpendicular to the polarization, and it's anisotropic. So the splitting is different if we consider the direction ZA and ZU in the plane perpendicular to the polarization, and this reflects the hexagonal symmetry of the crystal. And the most important part is that if we consider fixed electronic, fixed binding energy. We have a Fermi contour, and the Fermi contours are predicted to show these two star Rashba bands, let's say, in which by changing the ferroelectric polarization direction, we change the chirality of the spin. So once again, we find back our ferroelectric control of the spin texture. What we did is to find an experimental way to show this link. So we employed spin and angular result emission spectroscopy, also called SARPES, in two films that show spontaneously two opposite ferroelectric polarizations. So we found a way to stabilize either inward or outward polarization in germanium Telluride films by creating either a germanium or a tellurium-rich surface. And what we measured is the spin result band structure in the electrosynchrotron Trieste. So we operated in this way. So these are the results for one film, and we operated in this way for both of them. So we measured the band structure along one direction, for instance, ZU, and we obtained the two bands, B1 and B2, that are bulk bands, B1 and bulk band B2. And we then measured the spin polarization in the perpendicular direction, of course, because we have this P momentum locking, so PX, or P along ZA. And this is the result. So we measure that the polarization has two peaks with opposite sign. And the first peak corresponds to the bulk band B1, the blue one, and the second peak corresponds to the bulk band B2, this one. So we are changing the binding energy at this K2, and we obtain two opposite spin. We perform the same for an opposite value of the wave vector. So you obtain this time a positive peak for the blue band and a negative peak for the red band. So to visualize this, this result, we drew some arrows on top of the constant energy map. So we have our star, and we obtain two circulating Fermi contours that are opposite for the inner and the outer band. The blue one is the outer one, and the red one is the inner one. So this is the result for the germanium-rich surface. We operated the same way for the tellurium-rich surface, and we obtained an opposite circulation for the inner band, for instance, anti-clockwise, compared to the clockwise of the other film. So this is the first demonstration, experimental demonstration, that if we change the ferroelectric polarization in the Rashba system, we obtain a reverse spin circulation in agreement with the theoretical calculations. So once we have demonstrated this link, we then tried to control the ferroelectricity of this semiconductor. So in fact, this point is quite crucial in this case. It's not like in a perovskite, which is well known. If we have an insulator, we can switch it for polarization. In this case, it's more complicated because we have a ferroelectric semiconductor with very high density of free carriers. When we apply an electric field, we expect that the free carriers would screen it and prevent the polarization to switch. However, we have seen that by applying magnetic field, an electric field, the polarization can switch, and this is due to the fact that by switching, it would move polarization charges that will themselves counteract to the electric field that is applied. So it can also be a possible mechanism to screen the electric field together with the free carriers, and they both are happening in our system. So how do we control the ferroelectricity in a semiconductor? So if we consider ferroelectric capacitor, what is done normally is to apply a voltage between the two plates, for instance, a voltage path like this, and invert the ferroelectric polarization. And we detect the polarization inversion by monitoring the displacement current through the capacitor. And the displacement current will show a peak corresponding to the instant of the ferroelectric polarization change, thanks to this formula. However, in germanium Telluride or in semiconductors, this is not applicable because this current is orders of magnitude smaller compared to the conduction current that we have through the capacitor. So we designed a different way to control the ferroelectricity in this case that it's intimately related to the semiconducting property of this material. So we consider, for instance, GT in contact with a metal. Depending on the polarization, we will have either accumulation, depletion or accumulation of holes at the interface. And this will modify the bending at the interface. So if we measure then this conduction current through the interface, this will depend on the polarization vector. So we will have either a lower or a higher conductance depending on the states. And this is called bipolar resistive switching. We observed this in our films, and we separated the writing and reading operation in this way. So we applied a voltage pulse, for instance, a -1, negative like -10 volt, to stabilize up polarization. And we measured after the pulse the conductivity, so the IV curve at low voltages, for instance, up to 1 volt. And we obtain this curve. If now we observe, we invert the polarity of the applied voltage pulse to stabilize the other relative polarization, so the inward, we observed, we measured again the IV curve in remanence, and we obtain a high conductance. And these curves, we can switch reversibly between these two curves by changing the polarity of this voltage pulse applied. And actually, if we change it step by step, we can recover this hysteresis that resembles the one of a ferroelectric material. Also, we can switch up and down several times with an endurance up to 10 to the 4 cycles that is quite large and comparable to flash memories in the market. At this point, we want to know if we are really observing something related to the ferroelectric polarization change or not. So are we switching ferroelectric domains? This is the question. So to answer this question, we designed a different experiment in which we combine this bipolar switching. So we have exactly the same configuration as before, but this time we made the capacitor with the contact dynamometer thing, so that by means of an AFM tip, it was possible to measure the piezoelectric deformation of the germanium telluride film and map the ferroelectric domain distribution. And this technique is called piezo-response force microscopy. So we can measure the domains while we are switching the resistance. So here again, we have the ferroelectric, the hysteresis loop of the resistance. And what we did is to actually map point by point. Here we show you only a few. What happens to the domains. So we start from point A, 8 volts, and we have outward and inward polarization. So we have mainly blue state, let's say. And then we go towards the negative voltage, and you see that the domain distribution is changing towards the red state, which is obtained in point D. And so it means that we have, while we go from a smaller to a higher resistance state, we are also changing the ferroelectric domains. If we take the average of all these maps, we obtain the real ferroelectric hysteresis loop that overlaps to the resistance. So this means that we actually can change the ferroelectric state of our material and can read it electrically by means of a gate. And this achievement was fundamental for us to then try to measure the spin charge interconversion properties and see if we can switch them by means of a ferroelectricity. So to do so, we combined once again the possibility of changing the polarization of the material by means of a gate, together with spin pumping at ferromagnetic resonance technique. So we use iron as a spin injector and as a top electrode of our system. And at the same time, while changing the ferroelectric polarization, we are also measuring the spin to charge conversion efficiency. So here you can see that the conductance of these capacitors, so iron, germanium telluride, and silicon, is changing reversibly between two different states. So we have high and low conductance. And at the same time, for instance, if we take the high conductance point, the blue point corresponding to inward polarization, we have a positive spin pumping peak, so a positive charge current production. And if we change to the other state, that is the outward state, we get a negative charge current production. So this means that we are changing ferroelectricity, and at the same time, we are getting different spin to charge conversion signs. And if now we consider different crystallographic directions, because our band structure is not isotropic anymore, it's not circular, we have some star that depends on the crystal. What we observed in this time is that for a fixed polarization state, for instance, the blue one, we obtain a positive or negative peak, depending if we are injecting the current along ZA or ZU. These are the two perpendicular directions in the plane perpendicular to the polarization. So we have another symmetry element that leads us to a change of sign depending on the direction of the charge current injected, spin current injected. And the last point, very important remark, is that this switching can be obtained for all temperatures. I measured at 100 Kelvin because of experimental setup. However, I could also obtain the same result up to 300 Kelvin. So this means that for the first time, we have spin charge conversion controlled by ferroelectricity operating at room temperature. Plus, considering that it's silicon grown directly on silicon and compatible with CMOS, then we can really move towards this ferroelectric spin orbit logic device. And concerning now the conversion mechanism in this case, we have two different possibilities. So initially I was thinking about the Rashba effect, that is the main mechanism happening in two-dimensional electron gases. So just to recall you, when we inject the spin density, the two Fermi contours move in the opposite direction, forming a delta K. So we have spin to charge conversion or vice versa. And the conversion efficiency is given again by the Rashba coefficient that we expect to depend in germanium telluride by the polarization and the wave vector, as we have it's depending on the band structure. However, in our case, we don't expect this effect to be at play because in germanium telluride, when it's interfaced to the iron, we have a suppression of the surface states, the surface Rashba states, and we measure this, and also it's proved by density functional theory calculations. So even though by inverting the polarization, we can expect different spin charge conversion because we are changing the direction in which we are changing the chirality of the spin of the spin texture. In this case, it's not applicable. So it must be another mechanism. And what we found is that intrinsic spinel effect is more probable to be at play. This effect, to be very short, consists in the reversible conversion between a charge current and a spin current that can be seen as the appearance of an anomalous Hall velocity. So we have some sort of Hall effect in our material that depends on an internal magnetic field. This internal magnetic field is related to a quantity called the spin-dependent Berry curvature omega of K that can be calculated from the band structure. So we expect that since the band structure is modified by the polarization and depends on the crystallographic orientation, this effective magnetic field will be different depending on these quantities. And the figure of merit in this case is given by the spinel angle, which is can be computed from a tensor. The tensor is called spinel conductivity tensor, sigma, that depends on the direction of the injected charge current, for instance, X, and the direction of the detected spin current flow, so Y, and the polarization of the spin, that is Z. So depending on the geometry of the experiment, we want to consider different tensorial components. Where in our case, our collaborators computed this sigma tensor for germanium telluride thin films, and what I found is that the component that we are measuring with the spin pumping changes sign depending on the ferroelectric polarization. So if we invert the polarization, we have an opposite sign as shown here of this tensorial component. And if we now change the crystallographic direction, we change the tensor component, and by symmetry, they are giving an opposite spin charge conversion. The last point is that the predicted amplitude is also compatible, and sign are compatible with our experiment, and leads to a guess, let's say an estimation of the spinel angle in germanium telluride of 1%, which is quite large compared to other bond systems. And so with this system, we can obtain for the first time a room temperature ferroelectric control or spin charge conversion in a CMOS compatible semiconductor. And I would like here to, in the last slide, to make a sort of comparison between these two systems, which I talked a bit long about. So let's start, for instance, from the transport point of view. We have quite high mobility, two-dimensional conduction in the two-dimensional electron gases, of course. Whereas in first, at least in germanium telluride, we have a 3D conduction with quite low mobility because it's quite difficult to control the defect concentration in this material. Concerning the ferroelectric polarization, instead, we have quite robust ferroelectricity in germanium telluride with very high polarization charges that are really higher compared to what is observed in two-dimensional electron gases. For instance, 2.5 microcoulomb centimeter square in calcium STO in saturation. So this is also linked, if you want, to different amplitude of the Rashba splitting. So we can have a really giant splitting in germanium telluride that is giant compared to what is observed in oxides. However, in both of them, we have quite large spin charge conversion. In the case of the ferroelectric Twodimensional, we have a Rashba-Edelstein effect, which shows record Rashba-Edelstein length, and this is due to the fact that high mobility amplifies the Rashba splitting effect, so the alpha parameter, let's say, to give very long Rashba-Edelstein lengths. And in the case of first, what we have is, okay, we don't have very nice conduction, but we have a giant Rashba. So this is the main difference I can see. And then the last point is the operating temperature. So on one side, we are limited to 50 Kelvin, and the other side, we can reach the 300 K. But I want also to remark that ferroelectric Twodimensional in oxides actually are really promising because you can, as you saw, tune the perovskite, which are very flexible platforms, to introduce new degrees of freedom in the Twodimensional. And on the other side, in FERSC, what is important is the CMOS compatibility, and there is a lot of work which is done in this kind of materials to make it really suitable for applications. And the future challenges that I foresee is the demonstration of the electrical spin injection, which, because so far I've shown only spin pumping measurements because the FISO is based on spin injection. However, the converse mechanism would be great too. And we want to improve the switching efficiency and prove that we can get really a scalable device. And so this is really my last slide, just to recall what we've seen today. So the main message is that if we have a ferroelectric Rashba system in which these two mechanisms are intertwined, we can achieve in-memory spin computing architectures. For instance, the one called FISO that I introduced before. I would like to thank all the collaborators and people I worked with that are really a lot. I'm glad I worked with all these people, and in particular Politecnico and Senera Stales, but also Elettra, University of Vanley, and L'Aquila, the Synchronotron Soleil, SpinTech. I would like to thank ERC Preschool for funding the project. And of course, thank you for your very, very kind attention.
All right. Thank you so much for your excellent talk covering really a spectrum of interesting topics and really convincing that probably this is one of the future possibilities, to solve the power issue. Okay, so on behalf of everyone, I clap for your excellent talk. Now I request everyone to switch on their camera so that we can take a group photo, and then we will take the question answer. Yeah.
I stop sharing?
You can stop sharing, yeah.
Okay.
For a second, yeah. Good. So I will take maybe 10 seconds to... Swagata and Sijanya together. That's the reason I was wondering where is Swagata. Okay. Good. All right. I will wait 5 more seconds because still some people have not turned on their camera. Yes. Now I see that. Okay. So I'm taking now a photo. You all can smile. Cheers. All right. One more. Okay, so I think we did that. So I now request all of you to turn off the cameras, and Sarah, you can share your screen again. And if there are questions, kindly raise hands or write in the chat box in case you want to you want me to read it. So maybe I can begin with some very simple questions. In the beginning, those 2D gases with H2O and I think aluminum oxide, or you call it LOX because there is stoichiometry is always with L2O3. How did you prepare that? Was it all by MBE or?
No, sorry, but my laptop is not allowing me to change slide anymore. But anyways, I can answer. No, they were grown by sputtering at room temperature.
Okay, all by sputtering. So the H2O and the LOX.
Okay. The only exception is the Rashba bands were observed in the case of aluminum was deposited by MBE because it was deposited in situ at the synchrotron. So there was an evaporator cell there, and we just put 1 Armstrong of aluminum by MBE on top of the KTO. And yeah.
On top of what?
We always use the sputtering.
Okay.
Except the case of the sample that we used at the synchrotron to measure the band structure.
Okay.
In that case, we use ME.
Okay, but so the strontium titanate you can also deposit by sputtering?
No, the strontium titanate is the substrate.
Okay, so the H2O was just the substrate.
Yeah, we start from the substrate that is the KTO or the STO, depending on the system, and then we just deposit the overlayer to create the 2 leg.
And I mean, it's always when you start with the substrate, the surface is a bit contaminated, isn't it? And here you are really looking for clean interfaces. So
yeah,
do you really take care of some kind of cleaning or sputtering out of the substrate?
No. Depends what you want to do. For instance, if it's for transport, no special techniques are used, in the sense that we just need to reduce the tantalum or titanium. So
okay.
You don't need very clean surface. But it's true, if you want to observe the bands, you need to have a very, very clean sample. So what we did is to annealing vacuum for not very high temperature, of course, because it's a problem for the oxides volatility, but yeah, sufficiently high to remove all the contaminants, and then we deposited the aluminum and then we measured.
Okay, thank you. If there are questions, kindly raise hand. I don't see because your talk was very clear.
Maybe I can kill everyone.
Yeah, there is one hand. Yeah, Pranav.
Hello.
Hello.
I was just wondering, if the substrate is STO, then how can you say that it's CMOS compatible?
Yeah, indeed. Okay. You're saying that STO is CMOS compatible? No.
It's just as far as I know, STO is not a CMOS compatible.
Yeah, indeed, it's not. What I was mentioning is that maybe I was very unclear. Sorry. Is that the chalcogenides, so germanium telluride and this family, are directly grown on silicon, so they are compatible. Okay. Instead, that STO is more difficult to integrate in CMOS technology, mainly not because you cannot grow it on silicon. It's shown that you can do it if you use a specific buffer layers, etc. But the processes are not compatible with CMOS technology because you have to use PLD, for instance, so high temperatures and all this stuff. So you cannot use it with other semiconductor technologies.
Okay, all right. Yeah. So in the case of silicon substrate, are there any work which show this 2D electron gas or grown on silicon?
Good question. No, normally you can have 2-dimensional electron gas in using, for instance, gallium arsenide or making interfaces with semiconductors too. But you lose the advantages. Let's say you don't have all the advantages of the perovskites. Let's say.
Right.
So it's difficult to have a ferroelectric TODAG in this way. But
okay. All right. Thank you.
Yeah, thank you. I think Savat and Sijani, they are having some questions.
Hi, Sara.
Hello.
I will forget, so I will ask you the question. We can discuss later. When you do the BMR and QMR analysis from the the data, let's say for your case it is oxide-based Rashba, so you really do not care about the conventional spin orbit torques. But let's say if you have metallic Rashba, is it possible to separate out the contribution coming from the spin orbital effect and the Rashba effect? I mean the conventional spin Hall effect and Rashba effect.
Okay. I think with the spin Hall effect, you cannot measure. I don't know. Maybe I'm wrong. Albert will confirm. I think with this technique, you will not measure.
Why I asked you, because I see like in let's say my sample, like metallic samples, when I flow the current in like positive or negative direction, I have a difference of the Hall resistance when I do the in-plane angular dependence resistance measurement.
Because
so I have a finite difference instead of 0.
Yeah, but because you have a ferromagnetic layer on top, but we don't have any ferromagnets. So I mean, it's the same technique. You are applying a magnetic field, rotating but you want to prove something different. You want to prove the spin orbit torque coming from either Rashba-Edelstein or spin Hall effect. So both are possible. But in our case, we have only the TODAG, which is no magnetic in principle. And we don't have any magnetic layer on top in which we can induce any torque. You know what I mean?
Okay.
It's really, we want to just probe the spin density in the TODAG. It can be used also in the germanium Telluride. I mean, everywhere you have spin density formation by Rashba-Edelstein effect, you can apply the magnetic field in the plane and try to measure this magnetic resistance. And the spin Hall effect, you will not see it in this way. But you are speaking about the torque, which is another thing.
Yeah, okay, I got you. Okay.
Sorry, if you want to discuss later.
Yeah, we can discuss later.
Yeah, I mean, just to comment on this, Sabat, I mean, 2DEX, of course, it is complicated, but if you have other like grown films, and basically, as I understand, the Rashba-Edelstein effect is more interfacial, and the conventional spin Hall effect is kind of bulk. So if you make a thickness-dependent study of the high spin orbit coupling material, like topological insulators or something else, then probably you can comment if it is from the interface or from the bulk. So I think there has been similar work done, but for 2DEX, I don't know, because it's kind of fixed once you grow it. So am I right, Sara, or not?
Yeah, but yeah, I think what Shogoto wants to measure is the spin Hall effect or Rashba-Edelstein effect contribution to the torque, right? No.
Yeah, exactly. My point was like, how do you separate the two contribution from this analysis, like effect coming from Rashba or effect coming from, let's say, from the spin Hall effect? Because they can contain both. Let's assume that you have a sample, you have a system like platinum, then a ferromagnet, and then on top you have copper oxide. So then you will have both the effect, like you will have some Rashba interface generated on the copper oxide interface, and then you will have a conventional spin Hall effect source in the platinum like platinum cobalt interface. So in those cases, how do you separate them out?
Okay. In fact, the model applies to non-magnetic systems in which there is effect. It's another model. Okay. You want a model for the spin torque, which is not what we are measuring. You know what I mean?
Yes.
Yeah. Okay. This is a similar technique to measure the spin density in the Rashba system, and we are not creating any torque anywhere in principle. So the model is related really only to this. There is only the Rashba system. There is nothing else.
Yeah. Okay.
Whereas you
Okay.
want a model to extract the spin torque measurements.
Yes.
And maybe you can
Thanks,
do it by using this field like and tandem field like. I know there are mixed in the end. I mean, you cannot associate one to spinel effect and the other one to the Rashba snake, but maybe there is some model.
We can talk later. It's fine. Thanks.
All right. Thank you, Swagata, and thank you, Sara. So I think I see no more questions, and it's kind of about time. So I would share my screen and present this small digital memento. Do you see my screen, Sara?
Yeah, sure. Oh, nice.
Okay. So it's a small token of appreciation. I will send you by email later on. I will read it for you right now. So W2S seminar webinar series on spintronics, National Institute of Science, Education and Research, NICER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Dr. Sara Varotto from Siena Thales, France, and Politecnico di Milano, Italy, in recognition and appreciation for being a valuable speaker to give a lecture on Rashba systems for in-memory spin computing. So thank you very much for your excellent talk. We really enjoyed very rich physics, and I'm glad people would have learned a lot. And if there are further questions, we can come back to you at some point of time. And I hope to see you around in future talks. And definitely please join the 100 talk, which will happen in a couple of months. So with all this, I wish you all good night, good day, whatsoever, wherever you are. And see you next week when Thursday, Professor Kevin Garello will give a talk. So with this, take care. Thank you so much, Sara.
Thank you. Thank you all.
Have a nice day.
Bye.
All of you. Good night or have a nice day. Bye-bye.